My talk is a method for the automated discovery of angle theorems. This was motivated by a referee who suggested that they would like to see more problems addressed by the geometry expressions angle engine. In fact, they'd like to see hundreds more problems. The geometry expression angle engine considers an angle to be the difference in the direction between two lines. Now, of course, you have to be careful when you go through 2 pi, but geometry expressions is careful. And the direction of an angle bisector is simply the average of the bisected directions. The base of an isosceles triangle has the direction which is the same as the external angle bisector of the apex, and a reflection is simply a bisection viewed from a different direction. So applying this to a problem from Archimedes, we create a linear system that, like this. The first row of the linear system corresponds to one isosceles triangle. The second row corresponds to another, and the third row corresponds to the given angle. We can then solve this linear system for the difference in directions between lines 4 and 3, which is what is required. So my plan for creating hundreds of theorems was to look at the matrices of some theorems that I liked and see if I could create similar matrices and then derive theorems from those matrices. So this matrix, each row corresponds to an isosceles triangle, which is implicit in the fact that the lines are chords of circles. The rows, some of these rows could be reimagined as angle bisectors, and that would give us a different theorem with the same matrix. Here's another matrix where every row corresponds to an isosceles triangle. However, in this matrix, 2 of the rows are actually reflections. The interesting thing is that while the matrices are different, the location of the non-zero elements is the same. Now, of course, that location depends heavily on the order I used to label the lines in the theorem. In order to have a shape descriptor for a matrix which is less dependent on order, I go to graph theory and define the shape hypergraph of a matrix to be a hypergraph whose vertices correspond to the rows of the matrix and whose edges or hyperedges correspond to the columns, and which has an incidence matrix with non-zero values in the same place as my matrix. So for example, here's a matrix, here's an incidence matrix with non-zero values in the same location, and here is a hypergraph with that incidence matrix. So if we look at vertex 1 of the hypergraph, that corresponds to row 1 of the matrix, and we see that it is incident to edges labeled 1, 5, and 7. That corresponds to the fact that there's a non-zero value in column 1, 5, and 7 of row 1, this hypergraph. The 5th column is unusual because it has 3 non-zero elements instead of 2, and so it looks unusual in the hypergraph. For this graph, we have a hypergraph with two half edges, and those half edges correspond to the two columns which have a single non-zero entry. However, if we rephrase the problem slightly, we can merge those two columns to give us a matrix whose hypergraph is actually a true graph. In the case where this is where we have an actual graph, we're going to call this the shape graph of M. Now, a couple of standard graph theoretical properties that this graph has is one is Hamiltonian, so there is a cycle which contains every vertex, and secondly, it's cubic. All vertices have three incident edges. Now, if we have a graph, if we have a matrix with a shaped graph, then every edge has exactly every column of the matrix has exactly two non-zero values, and we can define a directed edge weight on the graph to be the negative of the ratio of the two non-zero elements, where we take it in the direction indicated by the directed edge. Now, given this definition, we have the following theorem. If we have a matrix with a Hamiltonian shape graph, the row space is linearly dependent if and only if the product of the directed edge weights around any cycle is 1. Now, this is important because linearly dependent row space means that one of our conditions can be derived from the others. In other words, this matrix describes a theorem. To prove this, we can take a Hamiltonian path. This gives us a set of linearly independent columns of size n-1. Now, if our matrix does not have full rank, then there must be no other independent columns, and so any column can be expressed as a linear combination of these n-1 columns. We can apply Gaussian elimination to that statement and derive from that the edge weight criterion. Now, let's focus specifically on matrices whose every row represents a bisection of some form. In other words, every row has a 2, -1, and a -1 in some order. So we'll call that a bisection matrix. And we can see by definition it's cubic. Every vertex does have degree 3. There's the following corollary to our theorem. If we have a bisection matrix with Hamiltonian shape graph, then the row space if the row space of M is linearly dependent, then its shape graph has only even cycles. That is, in graph theoretical parlance, it's bicubic. Now, the proof for the edge weights are going to be -1, 2, or 1/2, and you can't multiply an odd number of those together to give you 1. And here we see the number of bicubic graphs on a number of vertices. You can get this from Wikipedia. So we've seen that our shape graph gives us a visual representation of some of the information in the matrix. It shows us where the non-zero values are located, but it doesn't tell us which ones are 2 and which are -1. For that, I'd like to decorate the shape graph with some arrows. I'm going to put an arrow representing every 2. It's going to be an arrow from the row that the 2 lives in to the column. So for example, the arrow here shows that a 2 lives in row 5, column 4, as we see in the picture. Now our our directed edge product criterion around a cycle can be viewed visually in the following way. If you traverse a cycle, you will meet as many arrows pointing in your direction of travel as pointing in the opposite direction. This graph is a bicubic, and it's the only bicubic, as we've seen. There is only one bicubic on 8 vertices. It's more normally seen living in 3 dimensions as a cube. And this is the arrow configuration for that theorem. It begs the following question: how many other ways can you arrange the arrows and maintain that cycle property? It's a good recreational math problem. I'll give you the answer. The answer is 33. But if you remove symmetric ones, it becomes 4. These are the 4 different ways to arrange those arrows. This one, as we've seen, belongs to this theorem. This one belongs to the other theorem I started with, and we can invent theorems that correspond to the other 2. So at this point, I wrote a Mathematica program which takes as input a bicubic graph. It creates all the possible bisector matrices which have that graph as their shape graph, and tests the cycle criterion, keeps the ones which satisfy that. It then creates the graph automorphism group and applies the elements of that group to the different matrices so that it can remove redundancies. And I can report the essential matrices for different numbers of rows. For the 6-row pattern, there's 1. And here, this A theorem corresponds to that. For the 8-row pattern, we've seen there are 4. For 10 rows, there are 2 different bicubic matrices. Here's one, and here are the bicubic graphs. Sorry, I meant to say. Here are the matrices that correspond to that, and here is the other graph and the matrices that correspond to that. For the 12-row pattern, there are 5 different graphs and 146 different matrices. Here's one of them, a particularly symmetric one, and it yields a particularly symmetric theorem. So having found a bicubic matrix with a bicubic graph with a linearly dependent row set, we can modify it, keeping that linear independence of the row set in a couple of different ways. One way is to remove a vertex and coalesce the affected columns. Another way is to remove a row and coalesce 2 of the affected columns. And in both those cases, we end up with theorem-bearing matrices. Here's an example of the second approach, and here's an example which uses both the first approach and the second approach. Now, what I want as an end goal to this work is the ability to generate theorems automatically. Given the matrices, I can generate inelegant theorems automatically that look like this. I consider everything to be an angled bisector and arrange them all in a bit filter paper like this. What is trickier is to come up with nice theorems representing a given matrix, and this is a topic for ongoing work. We do have some suggestions. Use circles to reduce the clutter. Use isosceles triangles for variety. Exploit symmetries of the graph in your theorems, and perhaps reduce what you've got. So revisiting the question of why, not just to satisfy a reviewer, if we can generate Sudoku problems of a given difficulty, why not geometry proof problems? Thank you very much.